So today we're going to speak about neural networks, but in fact, I wanted first to speak about classical models, but these are very wide topics, so it took some time as well to prepare it. By the way, I'm kind of having personal maybe problems to implement it from the scratch. So today we are going to go to deep learning part, and I think it in some way will be mixed with the classical parts of our course. But okay, today is CNN and neural networks part. And yeah, today we are going to deal with the Catalyst framework, and that's my most beloved framework for training neural networks. I will speak about it a bit more later when we will come to the usage of this framework. And first, in this notebook, we just import everything we need. I think from basic course on machine learning, you have some thoughts on what is going on, like torch vision, and this stuff. That's why I won't stop on it. More than that is math time warnings, collections, everything, matplotlib, numpy, tqdm. I think it is common to you. Does anybody is there anyone who don't know what the TQDM is? If it is so, please react to the chat. Maybe I will speak about it a bit more. So today we will have we'll use CIFAR 10 data set, and it is from Torch Vision package data sets. Here we got a list of all data sets that is presented in Torch Vision, and really this is kind of baseline for computer visionist on neural networks. And we will work with CIFAR 10, and this is the data set of 10 classes, which is provided by Alex Krzyzewski, who is a PhD student of Geoffrey Hinton, who is another very famous and well-known machine learning specialist. By the way, Alex Krzyzewski is the author of the AlexNet, which we spoken about in a basic course. This was the first neural networks that was like a bomb. After that, everyone used neural networks. So the data set consists in 10 classes that you see here. We will see more about them in our notebook, but the thing to notice here is a very simple and all site. And for example, we have this is the main page for Alex Krzyzewski, and he used GTX 580 GPUs for his classes, for his work, and GTX 280. So it was really a long time ago. But still, as a task to train on, we will use it. So I think I will run it. Okay, I will restart it. We have everything clear. And I already downloaded it. locally, so it takes no time. And yeah, we see 10 classes such as airplane, bird, cat, deer, dog, frog, horse, sheep, and truck. It is kind of different classes, and this is what we hear, what we see here, and this is an automobile, this is an airplane, this is a bird. They have very low resolution, as you see, but still the class, one of them, could be really easily predicted by a human. So let's build our computer vision neural network pipeline. And let's first start from preprocessing, and we will use preprocessing that is taken from ImageNet dataset. Do you remember these values? Is there anyone not familiar with these values and where they came from?
3 colors, RGB.
Yeah, it's an RGB colors, and it is normalized RGB colors, but they came from an ImageNet. ImageNet is a very large database of images, which were very popular those years, like 2012 to 2015, 16 maybe. And most of the models are trained on ImageNet, and these means and STDs are kind of standard ones for processing visual data. Then the conception of transforms is already familiar to you, I think, and we will apply base transforms. It is for training and for validation. So we will end up with the same pictures that we started from, and augmented transforms are for expanding our data set. We spoken about it a bit in the machine learning course, but here is the implementation. So first we crop it, then we flip it horizontally with some probability, and then, for example, we could open it. Yeah, it is probability of 0.5. So we either flip it or not flip it, equally distributed. Then we use color jitter with hue, brightness, and contrast. And finally, we add base transforms to augmented transforms. And we move it to compose function, so we get the transform right. And the next step is we create training and validation data set. In our case, it will be we will use train part as a validation part, not thinking about more precise splitting, and apply these transforms. So next step is data loaders. I think it's very familiar to you. And we will end up with the batch size and 3 dimensions for images. So another function to illustrate our data set. And here we have, some horses, some birds, automobiles, and so on. Then we define our device as we usually do, and it is CUDA in my case, and then some model which looks like VGG. VGG and ResNet was 2 networks that changed the game in computer vision, in neural networks computer vision. They both of them halved the test error on ImageNet dataset classification, and that's why they're very famous and they are used till current time. But in my opinion, VGG is not very sufficient to use like in production. But ResNet is okay, and many neural networks use ResNet, or maybe some derivatives to perform to solve real life problems nowadays. So how should we make it? We make a basic convolution block out of one convolution, then leaky-relu, and by default here we have negative slope of 0.01. Do you remember the leaky-relu and negative slope parameters? Isaac wrote that he don't remember, but I think it was about something before. So if you missed something, you could type it once again. So do you remember what the leaky-relu is? So, someone?
It is a maximum of x or some small coefficient multiplied by x.
Okay, yeah. And it's negative slope multiplied by x. Yeah. So it is two linear functions, and that's how it is constructed. Okay. Then we apply Batch normalization, and in forward step we just move it one by one. Then comes the model, and that's why that's how we usually write our complex networks. So you decompose your code into more simple steps, and usually in neural networks we have some similar steps which we could put into separate class to make our code better and to make it more readable. Then what we do here is we first apply one convolutional block with max pooling, and the main body of the network is two convolutions, then max pooling, two convolutions, then max pooling, and finally one convolution and one adaptive pooling. Final classifier consists in dropout, linear layer, and relu and another linear layer. And finally, we apply everything we created one by one. So kind of simple network, but it uses this conv block for as a basic block. That's the main point of this class. Okay, let's define it. And let's use CIFAR summary. But yeah, here it has a wrong wrong. But okay, yeah, it's not broken. Broken is only the header is broken, but the body is okay, I think. Yeah. So here we have more detailed view on our framework. Yeah, and really nice visualization of our neural network. By the way, is it, yeah, it's a neutron up. Yeah, I have it here, and I think I will. I will show it a bit later. We have a really pretty visualization for created neural networks with this. I mean, to visualize your neural network, you could use this application, and it creates really nice results. We have to put the file of the model here, and this simple thing, Neutron app. I think you could. Yeah, I will put it. I'll put it here. We will use it a bit later to look at our neural network in this pretty format. But I have the Neutron app installed on my computer. That's why we will see it from a local file. I mean, not from the internet to have. That's kind of better. Okay, and what do we? Why don't I see? Let's make it this way. Yeah. Here is the simple representation, but we will have a more detailed view a bit later. And the total number of parameters is about half a million, and all of them for now are trainable. And our model has 37 megabyte. Oh no, it's multiplications and additions, so it is a number of operation. That's a different characteristic of a neural network. It is related to like flops. What we do with floating point numbers, and that's another measure of the complexity of neural network. Okay, then let's use a catalyst framework. And for now, we will use Logger, and they have nice interfaces. They really they work hard on their interfaces, and I participated it as well in creating these interfaces. And we have here iLogger structure, and we have a console logger from loggers, but also we could use, for example, another system for logging, such as MLflow, such as ClearML, or some folks prefer, for example, weights and biases, or Neptune AI. That's appropriate proprietary systems for logging. But for now, we will log into console, and for this system, we will speak about them a bit later. Here we have some formatting functions. That's okay. And from console logger, we implement our own logger. And the standard function here is as follows, but don't be scared about it. It's just a copy of this iLogger interface. So in fact, in more and more advanced deep learning and maybe software engineering, usually we refer to the source code versus the basics where we refer to documentation. So what I mean is most of the PyTorch is covered with relevant documentation. And it is done because it's a very basic instrument. But in case of Catalyst, we have a community of researchers, of some deep learners who just write these frameworks themselves. And this is a case for not for this framework, but for others frameworks too. And especially it is true for some state-of-the-art models, or maybe models connected to your thesis topic and so on. That's why I always prefer to read the source code, and let's look how we could do that. We go to the Catalyst repository, and all the framework is contained in into the directory with the same name, Catalyst, and that is true for many frameworks and for many libraries. They have also different directories and different files, but for now, don't bother yourself with it. It's totally not for us. So here we go to Catalyst, and let's move it. Let's move this to this point, and we have imported Catalyst core logger. So we go to core and we go to logger.py, and what we see here is this interface of iLogger. And yeah, for example, this is all the guys that I know. We with Xenia, we implemented MLflow logger as well as ClearML logger as well. So the iLogger has this interface, and what we see in our notebook is an exact copy of this interface. So it looks kind of complex, but in fact it's very simple one, because everything is split into sections here, and more than that, we could either use default values, which is provided, or we could put something that we want to have here. And the framework is kind of powerful thing because of this functionality, because of these parameters that could be changed. And we get different results by one code base. So in our case, we see that we just copied the default iLogger, and iLogger, I think it came from Java language, because in Java they don't have multiple inheritance. That's why they always use interfaces such as in form of abstract classes to implement everything. And yeah, by the way, this interface has many different methods that is similar to what we use, and it stands for metric for image, another interface for hyperparams. This is another part of the interface, and for artifact, which could be any file that we want to put into logging. So let's go here, and here we need to log metric. That's why we define such function. And here we have, for example, scope. And in this case, we have two scopes. When we are into epoch, and if you remember, usually we have written the following code for epoch in range of epochs, and did something here, and then for batch in, for example, loader, we did something like model of batch some outputs, and then loss is loss fn of outputs. This is what we did usually previously, and all this code is already contained in Catalyst framework. And here we have all the necessary points that is triggered. So we have one scope here is loader scope. So it is called when we call a new iteration of the loader. It's kind of here on epoch. Yeah, when we call new loader. And another scope is epoch, and yeah, this is really here. And on each of these epochs, we print some message. Let's, for example, add here loader scope, and then message. And here we have epochs. To the different, and also have this, which is just stores in console logger. So it basically Catalyst enables us to get rid of this code, this boilerplate code, which we use every time, and just concentrate on what we want to do. So, for example, we want to have a logger to console, and also we could have logger to TensorBoard, to another advanced logging systems, and so on. And this code is written only once, and we don't need to touch it anymore once it is written. And finally, we want to call supervised runner. This is how it looks like. Catalyst DL, that is the main package of the Catalyst. And supervised learner is our case. There are different kinds of learners, and also you could submit your if you solve some problem. And here we should put the input key and output key for our model. So Catalyst requires our data set to return dict, and in Catalyst, everything that is returned is dict with some keys. That's why we have a really nice structure of this. For example, input key, this is what is returned by data set. So in in a batch, which is returned by data loader, we'll have key of input key. In our case, it is EMG, and the model, we will provide this to the model, and model will output to output key of logits, and the target key, which is also returned from the data set, will be targets, and loss key will be loss. This will be stored into Catalyst by these names. Sometimes you want to make these things in different way, depending on what your model is. So we already run it. Then run this. Yeah, and here we have train and validation loaders, which we defined, and we put them to the dict. As I said, most of the things in Catalyst are dicts. That's why we want to make it dict. Then we sample model, criterion, optimizer, and everything. Let's make it. And then we call main function of runner.train. I will call it now to have the learning process started. And let's look what we provide to that function. So we previously defined the runner, where we put some keywords, and here we provide model, criterion, optimizer, and loaders to our runner, and also we provide our custom console logger. We train it for 6 epochs, and also we define callbacks as an accuracy callback. By the way, Catalyst has many metrics already implemented for us. Just check out documentation of the Catalyst. Yeah, documentation is stored here at the side. Yeah, it became more user-friendly some time ago, and the documentation is very similar to PyTorch documentation. They use the same style sheet, and okay, for example, the my lovely batch, my lovely part here is minimal examples. They are called minimal, but they are not so minimal. And here we have many things, starting from simple linear regression and multi-class classification, going to recommendation systems and computer vision, different computer vision tasks, including GANs, including Valle, which we will speak about a bit later in this course, and finishing in AutoML and config API. We'll speak about it a bit later, but many information is contained here. For example, we could have core submodel where we have callbacks, engines, runners, logger, metric, and so on. They have, yeah, they have this page of the architecture where everything is described, what means what, and where to start. I think these minimal examples that I already visited are really relevant things. You could open it in Colab and just play with it. But we will return to our stuff. So why am I haven't opened here? It was metrics, and here is. Let's just search for accuracy, for example. Yeah, we have callbacks, metrics, And yeah, for example, accuracy callback, AUC callback, CMC core, CMC score. This is the metric that is used in computer vision, and so on. For example, IOU is a metric for scoring bounding boxes, and so on and so forth. So kind of different metrics, which we could use from this framework. Okay, in this case, we just put accuracy callback, and as we did before, we put input key and we put target key to compare it and to calculate the accuracy. Another important thing is a logdir. Logdir is where everything is stored in Catalyst. This is usually done this way. So some local directory with name logs or logdir or anything you like. We will speak more a bit later. We will speak more about logging in Catalyst, and this is a directory that will contain everything. Then valid loader and valid metric is keys for validation. First, validation loader. In our case, it is validation, so valid like we put it here. And loss is validation metric, so we want to minimize loss value. Yeah, we minimize it. We want it to be verbose and load best on end. This is very similar to scikit-learn research CV, which is option of retrain. This is yeah, it just loads the very best model that we had during our training by validation dataset. So it has already trained. It had already trained, and this is how we. Oh no! Oh no! I have bad luck with cuDNN. Yeah, they want me to reproduce some code for them. Okay, I will do that a bit later, but in fact, it happened on the very last step. This is very not nice. Okay. I will check it out. So my machine has different type of cuDNN. I mean, 3 days ago, I just reinstalled my cuDNN because the version didn't meet the requirements for one of my projects. Okay, I think it won't stop us from having our way. Another, the next section will be about checkpointing and loading. Do you know how to load and save models in PyTorch? I mean, the official way.
We discussed it on the ML course, as far as I remember.
Actually, save state dict, right?
Yeah. This is what we do here, and it's the content of PyTorch documentation. So you don't forget it, then we won't stop at it for a very long time. So what we do here is we take catalyst checkpoint, just a bit. This is model state dict. Yeah, we load catalyst checkpoint, which is dict with model state dict, but also catalyst checkpoint contains more information. I think, yeah, I think I will have, since we have this error on the last step, catalyst already logged everything, and that's why we could run this code nicely and I think successfully. Then we have some code to validate the model. In fact, it could be done with Catalyst 2, because this is very boilerplated code. Like what we do, we move it to CPU, we extend it with some values, we go to model and put it to device, then softmax, then argmax, then everything. That's why it could be also done by Catalyst, but for now we will just do it by function. So, okay, and yeah, this is the way which is usually used in Catalyst to store modules. We have checkpoints directory. Let's look at it. Yeah, this is logs directory that we define here to save everything in logs, and this is.
Can I ask you a question on the previous one? So when you use decorator torsional grad
on the function,
yes, here in validation model you didn't say model eval. Is it already included into the torsional grad, or normally I did with torsional grad and model eval directly implicitly. So should it be done here or it's not necessary?
Yeah, in fact, it's I think it's it could be interpreted as an error here, because model.eval, or I prefer train false. This is how I do that, because usually I mean the less methods I have to remember, the better. And that's why I always use this, for example, train false, or I move to device, not to just CUDA, and so on. Okay, by the way, I have my own set of data science stuff, and usually I have such a function. Let me just open it, and okay, not in this project, but for example here. Yeah, I usually use this context manager when I do my stuff. So I guess you know what the context manager
yeah, sure.
is. Yeah, and this is how it looks like. So we define context manager, and I call it usually infer. It takes a model and it remembers the status, and then it goes to evaluation mode, and then with torsional grad we perform everything we want, and then we return previous state. This is how it works, and it could be also used. So if you need, take it, I will leave it here in the seminar and publish it. Yeah, this is very handy. I'm not. I didn't employed it to used as a wrapper, function wrapper. So in this case, we will have another if. For example, kind of function, so on. So this is the basic stuff in Python. I think if you want to use this decorator, you can. In case of this decorator, we could not use it as a function wrapper because we require the model. But still, it's very handy. I usually use that. Not to forget this. And in fact, this situation is why I always use frameworks in my work. Especially I use Catalyst, I don't use others, but others still okay. For example, Lightning. But yeah, this is kind of software engineering stuff, what to prefer, but I prefer Catalyst. And it already has all these small things that I don't want to bother myself with. Okay, here we just count our predictions and metrics for them. So maybe nothing more interesting. And yeah, I was speaking about the logs directory. This is the logs directory, and here we have first TensorBoard, but we in fact didn't put anything explicitly to TensorBoard, but Catalyst already have some stuff logged for us. So by default, logging to TensorBoard is enabled, and this is local TensorBoard logging. If you get your TensorBoard up and running, it will create some beautiful views for you, but I usually use more advanced instruments. And going to the logs directory, we have hyperparams in YAML file here for our supervised logger. It will load a bit, and yeah, here we had no hyperparams, but I think I could just. And why didn't we, just a second, why didn't we have any checkpoints? Then that's because my training failed. It was the first epoch. I mean, we haven't finished the first epoch.
I'm sorry, may I ask a question about
Yes, of course.
training model? You mentioned that it somehow related with grid search CV. Could you please explain it?
Oh, it's not directly related. It is kind of metaphor for that. So our runner, when it trained, will have a runner point model and the best model, which provided the best validation score, in our case, the minimal loss, will be loaded into that attribute of the runner.
Am I right that it's usual training process when we iterate over epoch firstly, and inside this loop we iterate over batches?
Yeah, this is kind of default value, and I think this is 99.9% of training. Yeah.
Okay, and in each step we upgrade our weights of our model, and we store it somewhere and compute accuracy with these weights.
We do that in every epoch, on every epoch. By default, I mean, the epoch is one cycle over all the data set, split it by batches. Yeah.
Yes.
And we usually perform validation on each epoch. It is default value, but we could change it to have validation less frequently. For example, if it takes lots of time, this is the case. For example, I have a validation every 5 epochs or so.
But the best model is supposed to be at the end of our training process.
No.
No, it's not necessary. It might happen in the middle, in the beginning.
Yeah.
We can overfit after that.
Yeah.
Okay, I see. Thank you.
I mean, you don't know beforehand when will you overfit. So, for example, you have your machine loaded with the training, and you think that, for example, 20 epochs will be enough, and you put this number bigger than you require to be not overfitted model. And if your framework, like Catalyst, chooses the minimal validation loss function in our case, or any metric, it takes this for us and it stores it in this file here, this
yes.
file.
Okay, I see. That's how it's related with grid search. It's it's a way not to overfit our model.
Well, kind of, yes. Yeah, I mean, that's a metaphor. That's not direct. They're not directly connected. But yeah, in the grid search, we usually have a number, like we have model retrained on all the data with optimal hyperparameters. And here we just have optimal from validation loss point of view, model saved to fixed file best.pth. Also, we have files named best.
One more question. As I understand, we don't necessarily need to have the same loss function in validation metrics when we choose best model. It can be different, right? It doesn't need to be differentiable even.
Yeah, it could be metric. And even it is called metric. Yeah. So we could have, for example, IOU for computer vision task. We could have accuracy. We could have F score, anything. And this is implemented in Catalyst. And if you want something more experimental and more exotical, you could always implement their interface on this callback. For example, let's look at let's look at something kind of easy. Yeah, for example, dice loss is okay. And yeah, here we have base class of logarithmic callback, So we have different methods here implemented. Here is examples. And yeah, in this case, we just call our base class with AUK metric. And in this case, maybe more verbose. Yeah, for example, dice callback. yeah, and it is batch metric callback. So it counts metric. It is a callback that counts metric on batch. Usually classes in software development is called in this way. Is called in this way, and that's how to read them from right to left usually. But when you use something that you are familiar with, you first see the first word and you understand everything else. That's why it is the first word. Okay, so we have dice callback here, and it implements. We have rich example on using it. Yeah. And in this case, yeah, we also call dice metric, but this is just interfaced thing. I mean, you have default input values that you should provide, and in this class of dice metric, for example, let's for example go to for example catalyst metrics log segmentation. Place metric segmentation. Here we have segmentation, and here we have dice. Dice metric, which is region-based metric, which is another class. So this is real object-oriented programming. And yeah, that's what I wanted to see. I call back batch metric. So it all goes to abstract interfaces. That's why I like Catalyst, that it has very distinct abstract interfaces. And you could always go to this level of something that starts with I, and this is an abstract interface that you should satisfy, and in this case, your code will be compatible with all the Catalyst infrastructure. It's very handy when you use, like, in our work, we use like maybe 80% of default infrastructure and 20% of our own coded infrastructure. That's why I like these abstract interfaces, because everything is described here. All the parameters are provided. If you are not familiar with software engineering, it could look like something difficult, but in fact, it simplifies many things. By the way, you could always check out source code implementation, and that's not. I mean, it could be hard for the first time, for the second time, but for the 15th time, it won't hurt that much. I guarantee you that. So yeah, we could measure validation by different metric, and we could minimize it, we could maximize it, and so on.
One more question. I look at the layers in both model, which was VGG, and the next one ResNet. And in both cases, when we use convolution layers, we use no bias, so bias equal to false. Is that like by default in computer vision? Or...
Let's save it. Let's save it for the second model. I mean, when we go to it, okay? Just a bit. I mean, for everyone to be in the same context at the same page. So basically, this is way to do everything. Yeah, I will fix my cuDNN, and yeah, I think maybe do it on collab on other time. And another, speaking about logs, we have checkpoints directory, and here we have usually best.pth and last.pth, and usually also we have all the intermediate, like for example epoch 01 and so on. It is all adjustable, so we could specify how many points, how many snapshots of our training process do you want to have, because sometimes it gets really space consuming from the disk point of view. And yeah, finally we validate our model and it gets really nice results. So since it is a VGG-like net, that's the result that we expected from it, and a very simple data set. Yeah, and here's another part of our code, and here we have even two layers of simplification with functions. That is the first, where we directly use conv2d from neural networks package, and then we construct residual block. By the way, when I checked ResNet implementation in PyTorch itself, it has built-in implementation. It was very not user-friendly code, but here we have really nice piece of code. So what we do here is residual block is what you remember. Do you remember how residual block works? Anyone?
It has skip connections, if I remember correctly.
Mm-hmm. Yeah, it works in this way. We have a couple of convolutions, and we have skip connection. So first we take the data, then we convolve it, and finally we add the first the like identical transform and sum it and return it. And after that, after such block, we perform pooling, and we go on and on. So yeah, here we define convolution, then norm layer, then okay, then batch normalization, then activation, also convolution, normalization, activation. And another stuff is downsample. Downsample is pooling layer. And we apply it like this: convolution, batch norm, ReLU, convolution, batch norm. And if we downsample, we apply it and add identity, so the original value of x, and then we activate it. Yeah, the question was about this bias false. Yeah. Is it a standard for computer vision tasks? This is let me think a bit. Convolution. In fact, why do we have bias here? The answer is as follows. We have normalization layer right after the convolution. That's why we don't want our convolution to have some bias, because the batch normalization layer, the very next layer, will compensate it. So it will compute the moving average, then compensate it, and then replace it with trainable parameter, as you remember from batch normalization.
So in fact, we will use more parameters which will be useless, just takes more time for calculation.
That's one reason, and another reason, these parameters will be underspecified. I mean, they will be yeah, This is kind of regularization. I mean, every value of such parameter will go well because we will compensate it with batch norm. But by the way, there are for example, mobile inference, we have libraries that glue up this convolution and batch normalization, for example. So if we have let's just have a nice example. Yeah, for example, yeah, if we have convolution and batch normalization, we could glue it up by multiplying. So we have filters in convolution, and we have mean and STD in batch normalization. So we add mean to all this, or we subtract mean from all this, and then we divide by our STD, and then we store only this filter, and we get rid of these two parameters from batch norm. And if we speak about layers that has hundreds of or neural networks having hundreds of layers, then we save a couple of thousands parameters. That's nice. If we speak about operations, we save them too. So we don't need to separately first convolve, then multiply, then subtract, then divide. We do it in one operation, and this is more computationally effective, and it is okay for edge devices.
One more question. When we use batch normalization, is it normal practice to use it just after convolution or after ReLU?
Before activation.
Before ReLU?
Okay. No, not ReLU, but any activation.
Oh, any, okay.
It is connected with the fact that activation function is usually have some irregularity at 0 point. That's why we wanted to normalize data before that. So, I mean, activation layer doesn't have any parameters. And we kind of adjust data dynamically by batch normalization just before this activation. So by training batch norm, we could move our activation up and down and so on. That's why we do that.
But when we use leaky ReLU, the parameter alpha is also optimizable, is it?
No, it's a hyperparameter. I mean, it's provided here.
Ah, okay.
It is from constructor. What you speak about is I don't remember how's it called, like adjustable ReLU or something of that thing. Is when we have, for example, the second part with another slope is a trainable parameter, but it's in fact it is used rarely because it doesn't provide any improvements over usual leaky ReLU. But I think they have some specific problems that goes well with this solution, but not widely used, definitely. Yeah, okay. Here is a residual block, and it is already kind of severe complex. It's a medium complex class, yeah. And here we go to, yeah, I will run it to have it. And here we have base ResNet, like a simple ResNet. Then what do we have here? We have make layer function with normalization, with downsampling, with strides, and here we call our block function to form residual blocks that we described above. And we return sequential of all these normalizations, then downsamplings, and everything. And so we wrap it one more time. And finally, we apply it here. So first, we create some just starting convolutions, normalization and ReLU, and pooling. This is to make feature map out of the image, and just to increase number of parameters of channels, because at the start point we have 3, and here we have, for example, like 64, for example. Yeah, 64 exactly. That's the standard for ResNet. Then we have max pooling, and then we have this. That's why we have written all the code above. I mean, usually in such networks, we just create some building block and then provide different hyperparameters to that block to have different implementation. But it's very it is very time consuming to adjust all the shapes. So usually you get, if you have, for example, some convolutions that are not powers of 2, that's in this case you could have some bad time. But in fact, adaptive average pooling saves us all, because it creates object with the same size, and this could be put to linear layer with predefined number of parameters. And here, in fact, we have a fully convolutional network, classical fully convolutional network. When we go from convolutional part, then we apply this adaptive pooling layer with 1 by 1. So we only have channels, 64 channels, and we have 1 value for each channel. And here, after that, we apply linear layer. Okay, that's just addition of initialization, different kinds of initialization, but usually that's not a very big deal, because default initializations are good for most cases. If you are not a researcher in this field, don't bother yourself. Then forward is just we apply every layer sequentially. I usually prefer to put this into an n.sequential final. And for example, I usually inherit not from an n.module, but an n.sequential. And in final part of my constructor, I do that like I don't put it to self, I put it just to variables, and then I put all them to a big list, and this list goes to super dot init of in fact of sequential, and it saves me this boring forward function. That's what I recommend to do if you write your code, but it works fine as well.
I have a question.
Mm-hmm.
Can you explain what the parameter block is? Like we have this in the make layer, we have the parameter block and blocks. Like
you mean this?
Yeah, these ones. And what's the difference between block and blocks? And actually, what is that? How should we provide it? Is it a list of the layer names, or what's that?
Yeah, okay. Let's, for example, let's look at how we use this base ResNet network. Oh yeah, I remember. This is where we have this is where we have a homework, but yeah, still we have DenseNet. Let's look at this. We have the same block parameter here, and in fact, in this block is nn.module. This is a class for this variable. So in fact, this block is this class, residual block. So we would call it in the following way, like base ResNet of residual block. And other parameters. So this is the constructor for our block.
Cool. Okay, and this is we can pass only the one block.
For one instance of base ResNet, yeah, but we could have different. For example, we define dense block here, yeah, and we could pass it to ResNet with dense blocks. This is why we created such a parameter.
Okay, I see. Now it's clear. Thank you.
Yeah, this is Python, and that's why we wanna make fun out of it. I mean, it is in Python, everything is an object. That's why we could put anything to anything, then wrap it in anything, then maybe inspect. Maybe someone have heard about this model, standard model. If you didn't heard about that, check it out. I mean, official documentation of Python inspect model. It could, or for example, meta classes. This is another way to have fun with Python. But if you are not very experienced coder, or just at least medium experience, then I think it could be harder for you either both to understand and write it. That's why for the first tries, you could use just simple code, just one by one, code anything. And then if you, for example, write 5 different networks and you see that they are somehow similar, then, for example, cut similar part, put it to the class and permit with different parts. But that's more about software than machine learning division. Yeah. Here is the same ideas like dense block, bottom block, just blocks, and of them are used here in a dense net.
Vladislav, one more question.
Is
if you use instead of blocks, if you use, for example, cycle in forward method, would it be basically the same if you try to use the same blocks one after another?
Yeah, I see. Yeah, it will be the same. Then the graph, I mean, computational graph in PyTorch is created by PyTorch operations. So when you put some tensor to some module, and it goes out, it remembers when it came from, and it doesn't depend on inner infrastructures that you use. Either you use this like hard coding anything, or you just cycle it. More than that, nn.sequential, yeah, just not to be scared to go to, let's go to this repository and just check out how nn.sequential is implemented. Here we have a torch, but be careful with the with PyTorch repository, because in fact it contains lots of C++. And if you don't know, C++ in fact in advanced on advanced level, then you kind of won't be able, but many parts are human, like many parts are Python readable. So what do we have here is NN. I mean, I want you not to be scared about source codes of many things. If you don't know something, first go to Stack Overflow, like just to solve it and forget it, maybe, if you don't want to get some expertise in that. Then the second place is documentation, and if documentation keeps silence or is not enough for you, then go to source code. For Python, it is very easy. Then we want to go to init and look at sequential. We don't see it here. That's why we will go to modules. I just know that modules is for us, and sequential is not here. Just operational adaptive personalization. Sequential at it is .container. I mean, in init.py we usually have all the, not usually, but well, sometimes we have in init.py all the things, and I see that our sequentials that we're searching for is in container. Another way to inspect source code is have it locally and then search globally in all the project for what you are interested in. For example, like class sequential, and that would be string that will result in the definition of such class, and we want container.py, and here we have sequential, which is inherited from module, some really large and nice dot string. We have init, and what do we do in this init? And I will make it a bit bigger for you. Yeah, in init, first we initialize our module, and then what we do here is we just remember, like we add module and add module. And when we add module, what do we do? Not clear. Like, yeah, we just do it, and whoa, they use overload. This is very high level Python code. Very nice. Pum pum pum. Oh, I see. They, what do they module? Yeah, this is very advanced Python code. So they use overloading like this, and they use some magic to implement things. For example, let's go here. Whoa, my browser is almost broken. Yeah, and yeah, it saves everything to cell.modules. by name, by incremented number of names. So what do we have here for forward method? Yeah, this is a cycle. I mean, this is what I wanted to show. The nn.sequential uses for loop to implement it. Okay. Okay, so finally, the task for you for your home assignment is having all these blocks. You will need to go to this and to train your network to have 91% of accuracy of on validation set. I suggest to use it with to make it with Catalyst because it's really easy. You just have to copy everything, and if you are not sure about what to do, you could check out Catalyst documentation and examples. They have all the examples. The point here, yeah, no fine tuning, just training from the scratch. And then you will have to define run checkpoint.py, which load this state dict. State dict loading already written for you, but you could check out Torch documentation for that. And it runs checkpoint on validation dataset. So first it loads from this, then it runs on validation and return and prints what the final score is. And your submit will be these three files. I think I will send you another. Oh, just let's check it now. Torch Hub, it's called this way. I recommend you to use this tool. It is called Torch Hub. It is like a Docker Hub. If someone is familiar with Dockers, you build some image on Docker and you put it to the internet storage. And the same thing could be done with neural networks. So you train some network, then you push it to infrastructure provided by PyTorch, and you could load it from another place. This is a very nice thing, but remember about privacy. I mean, if you don't use it for your work, because it's not secure, but for publishing your research for our home assignments, it will be very nice to use this tool. And it could be used very easily from Torch. So the thing here is torch.hub. Let's look how this, yeah, torch.hub loads state dicts from URL. So you put it to URL and oh no, that's not what I wanted. So you use Torch Hub log, Torch Hub list, and so on. This is nice way to download and upload things with PyTorch. So I think that's all for today. Thanks for waiting.
Vladislav, finally, should we upload on PyTorch or should we upload to Stepic?
Speaking about uploading, I was speaking about the weights. So you could, if you want, you could put your weights on Stepic, but I'm not sure if Stepic could handle such big files. That's why I think you have to, but basically you have two ways. First, to store it somewhere. I mean, somewhere
on our GitHubs.
Well, yeah, that's one thing. Yeah, I think it's not, I mean, that's not what it made for, but I think, yeah, it will work.
But will you share more instructions or?
Yeah, I think
That's-
about publication of the module, I will share more instructions.
Okay, thanks.
Maybe
Mhm.
we will set up some Torch Hub
MSAI repository.
yeah, repository so you could push to it, or we could set up, for example, Min.io, which is S3 compatible storage. Well, I will think about it. For now, you could just save it locally. I mean, weights, your PTH weights, and do homework, and I think, yeah, during the weekend I will think about it and experiment a bit.
What's the deadline for this homework?
I think 2 weeks, just as usual.
Okay, thank you. And can I ask one more question about our course in general? Will it be shifted after the new year, or what do you think about our plans?
What do you mean on
Ah.
shifting? I mean, it will continue. Yeah, I think it will continue.
Okay, in this case, could you please provide some exact dates of our course in January, so we could plan our vacations and so on?
Yeah, I see. I think we will we'll make it generally available. I mean, for all the subjects, we will publish schedule during, so what do we have now, November? Yeah, I have sent the Netron app. We will speak about it a bit later. So we will publish the schedule, and yeah, I think before the next weekend, I think, yeah, something like that.
Okay, thank you very much.
Thank you.
Thanks, bye.
Yeah, bye-bye.
Bye.
See you next Thursday.